Hi, this video is going to wrap up our coverage of graph traversal with analysis. We've gone over the depth first search and breadth first search algorithms and how they work. Now we're going to see how efficient they are. So those two algorithms, depth first search, breadth first search, they're traversals. They visit every vertex up to once. And in this video, we're going to work out the asymptotic efficiency of depth first search and breadth first search. In other words, the big O runtime of those algorithms. Both of these algorithms use some data structures. There's the scene variable, which is a vector of booleans, and there's the to-do variable, which is either a stack in the case of depth first search or a queue in the case of breadth first search. There's also the graph data structure G that holds the graph that we're traversing. First, a quick reminder on n and m. Remember that the convention is that n is the number of vertices in a graph, and m is the number of edges in a graph. Our analysis is going to involve both n and m. So just keep that straight. N is vertices, m is edges. Also a note on the graph data structure for G, the graph. Depth first search and breadth first search only use one graph operation, which is the out edges operation. Out edges I is given a vertex index I, and it gives a vector or list of all of the outgoing edges originating at I. Remember that we studied two graph data structures. There's the adjacency matrix and the adjacency list. The adjacency matrix out edges operation is big O of n, which we consider to be kind of inefficient because it loops through every possible vertex in the whole graph to decide whether it is an out edge. The adjacency list is substantially more efficient on out edges. Out edges of I takes degree of v or degree of I time, so it's time proportional to the length of that list, the list that it produces, or the vector that it produces. So that's more efficient, and that has a pretty big impact on these traversals, since the only operation we're doing is out edges. Every iteration of that main loop does an out edges call, so it's really critical to traversal that the out edges operation is fast. So the adjacency list is definitely faster for graph traversal. So we're going to do our analysis based on the traversal process using an adjacency list. We're going to assume that the graph is stored in an adjacency list because if you want your traversal to be fast, it needs to be in an adjacency list. So that's the assumption we're going to make. Basically, if you're in the business of doing traversals, you should store your graph in an adjacency list. So we're going to break this analysis into two parts. We're going to analyze everything except for the seeing part. And the seeing part is the interior of this if statement. So, we've got the whole algorithm here with a while loop. And if we haven't seen next, then we do all this stuff. We visit next, set its flag to true, and there's that for loop to deal with the out edges. So first we're going to analyze everything except for that part of the algorithm, and then we're going to come back to that part of the algorithm. So dealing with those parts, we create the scene vector that creates an n element vector. Creating an n element vector takes big O of n time to initialize all the false values. Creating an empty stack. So, we've got a callback here to stacks, so you can review this if you want, but creating an empty stack is constant time. Pushing onto a stack is constant time, so constant time there. And then we have this while loop. And in the worst case, there are n iterations. If the graph is connected from the start, then every single vertex in the graph gets visited once. So the maximum number of iterations here is n, all vertices in the graph. And we do a stack top operation. Again, review your stack efficiency, but top is constant time, and pop from the top of the stack is constant time. So altogether, I've got big O of n to create scene, and then constant time for to do and push, and then an n iteration loop that takes constant time. Again, we're not counting the visit stuff yet. So constant time per iteration, and that adds up to a total of big O of n. So everything except for the seeing part of the algorithm takes linear time, big O of n. Now, in order to analyze that seeing part, we need to make one observation about the nature of these algorithms, which is that a vertex can only be seen once. It's just an important detail that's not obvious. So remember the logic of that if statement that decides whether to see a vertex says if scene of next is false, so if I haven't seen the vertex, then we do some stuff and then set scene of next to true. If you look at the pseudocode here, just focusing on those parts, if scene of next is false, then do something, and then set scene of next to true, and then do something. So when we see a vertex, we flip that scene flag from false to true. Every scene flag starts false When we see a vertex, we flip it from false to true, and it'll never change back. Once you see a vertex and set that flag to true, it never goes back to false again. Look here, they're set to false initially. There's one assignment that changes from false to true. There's no capability of ever going from true to false again. So this is a one-way trip. You start out unseen, you get seen once. That's the end of the seeing for that particular vertex. So that means that a vertex can only do that transition once, from seen to unseen once. That means every vertex V is seen at most once. A vertex might never be seen if it's unreachable, but if it's reachable, it gets seen once, and that's the end of it, never multiple times. So that's important to our analysis here. That means that this seeing process happens once per vertex in the worst case, maximum of once per vertex, not any more than that. So let's analyze how much time one of those seeings takes, and then we'll work out how much it takes for the whole algorithm. So just focusing on one execution of this highlighted seeing code, the if statement is constant time. We're assuming visit is a constant time operation. Setting a Boolean flag to true and a vector is constant time. We do one outEdges call, and that takes big O of degree of the next. This is where we're assuming that we're using an adjacency list. So this is big O of the degree of next time right there for outEdges. And then the for loop repeats once per outEdge. So there's degree of next iterations, and pushing into a stack is constant time. Again, review your stack efficiency. So altogether, we've got constant plus a big O of degree of next time plus a big O of degree of next time. So the bottleneck is big O of degree of next time. So one execution of this seeing process takes degree of next time. Now remember that every vertex is seen at most once. So the total time we spend in all of these seeing executions among all of the while loop iterations of the whole algorithm would be if we add up the degrees of all the vertices. And that's what this math notation says. It's big O of the summation over every vertex V of the degree of that vertex. That's the total amount of time we spend seeing vertices. So now we need to clean that up and analyze that in terms of just N and M. And it turns out there's an equation from graph theory that can help us with that. It's called the degree sum formula. It's sometimes called the handshaking lemma. And it says that if you add up the degrees of all of the vertices in a graph, it adds up to exactly 2m. So m is the number of edges. So if I look at every vertex, add up all of the degrees of those vertices, I'm going to end up with exactly 2 times the number of edges in the graph. Here's kind of a sketch of why that's true. If you start off with a graph with no edges in it at all, every vertex has a degree of 0. Degree is the number of edges touching a vertex, so if there are no edges at all, every vertex has a degree of 0, and this equation holds there because you have 0 on the left side, 0 on the right side. Okay, now suppose I've got a graph and this equation holds, and I add one edge from A to B. That increases A's degree by 1, and it increases B's degree by 1. So every time I add 1 to the number of edges, I add 2 to the total of all degrees, right? If I were to add another edge in this graph example over here, let's say I add a edge from 1 to 4. Well, let's see what we've got beforehand. So beforehand, I have 1, 2, 3, 4, 5, 6 edges, right? This equation says that if I add up all the degrees, I should get 6 edges times 2, which makes 12. Let's try it. 0 has degree 2, 1 has degree 3 for a total of 5, 2 has degree 2 for a total of 7, 3 has degree 3 for a total of 10, 4 has degree 2 for a total of 12. So in this example, that works, right? So far so good. Let's say I add one more edge between 1 and 4. Well, that increases 1's degree from 3 to 4. It increases 4's degree from 2 to 3. So I did a plus 1 degree there and a plus 2 degree there. So every time you add one edge, you add 2 to the degree total. So that's why this equation holds. Okay, so let's put this all together. Depth first search, everything except for the seeing part takes big O of n time. We worked that out earlier. And the seeing process takes big O of the sum of all the degrees in the graph time, and the sum of all the degrees in the graph is 2m. So the seeing part takes big O of 2m time. And we drop the 2 out of the big O notation and just say big O of m. So if we add those together, big O of n plus big O of m, that's big O of n plus m. So proportional to the number of vertices plus the number of edges. Now let's look at breadth first search. It's basically the same kind of situation. You remember the algorithms are very similar. So everything before the for loop here, or I guess the while loop, takes big O of n time to create all of these setup stuff. And then Every vertex gets removed from the to-do queue at most once. That's the same thing, same kind of idea as seeing. Every vertex goes into the queue once and gets removed from the queue once, and that's the end of it. So the while loop, is, aside from the inner for loop, takes a total of big O of n time, just similar to what we had with depth first search. And then that inner for loop, all the seeing, takes big O of degree of v time, which is 2m, which is m. So we end up with the same grand total, big O of n plus m time. So here it is, the summary of the asymptotic efficiency of these traversals. Depth first search takes big O of n plus m time. Breadth first search also takes big O of n plus m time. It's a pretty fast runtime. It's proportional to basically how much information is in the graph. The number of vertices n plus the number of edges m. And just to be clear, that's assuming that the graph is in an adjacency list data structure. These would be slower if you used an adjacency matrix.